my name is Tito Busani, and technically I teach at ACE, the 484, 584, the photovoltaic class. And here I am also the nanofab manager, and I'm a research faculty at the University of New Mexico. I'm responsible for what we call the nano lab, or the nanofabrication lab, and specifically the clean room where all the devices are fabricated and partially are also characterized. So today we will walk through the clean room. We'll show the different what we do in the clean room generally, and what means the clean room. Okay, so what we are doing now here is we are entering the clean room, and we call this area the gowning area. The concept of the clean room, like the name itself, is a clean environment, and the way we control the cleanness of the environment of the air is through three means. One is filtering the air. The second is reduce the pollution coming from outside, okay? And obviously the third is the behavior inside the clean room. So the largest pollutant for the clean room is the human body, because every time we walk from our skin, from our clothes, we lose particles. So in order to control the number of particles, we do what we say, we gown up. We put up clothes that they will keep inside all the contamination or all these particles that come out from our body, from our clothes. In this way, we keep the air clean, and the filter that they clean air, the longevity of the filter, which are pretty expensive, that they clean the air inside the clean room, is maintained through a long period of time. So now we are fully gowned up. As you see, I have UV protection goggles. I have all complete gown up, so there is no particle coming out from the body. I have my gloves. So now we are ready to enter in the clean room, and hopefully we keep it clean. So as now we enter in the clean room, and the first part you see is where the people leave their material to be used in the clean room. We don't allow external material to be used inside the clean room unless it's white, with isopropyl, and it's clean. We always require that people keep the stuff that they need to operate efficiently in the clean room, in boxes, under contamination control, and not leaving the clean room. One of the strong contaminants for the clean room is actually your finger and your skin. When you touch with your finger something, what happens? Any surface, you release some grease. So that's why the gloves, and that's why you don't allow other things coming inside the clean room from the outside, unless are white. So we divide the clean room in bay and chassis. So this part that you see is the first bay, where we have as I zoom in, you will see one of the recent tools, which is a dual ICP chamber that allowed 4-in and 4-in process. It is extremely useful for etching a nanoscale level material, and pretty much all type of material, 4-5 material, 3-5 and 2-6 material. You see some furnaces that are used, one is Turbidon, that are used for oxidation. This is specifically, they are running a silicon oxidation process. At the same time, behind this area, which is the clean area, and is the first bay, as you notice here, we have also an area that looks more dirty, where you see a lot of you see pumps, and you see gases and gauges. And this is what they call a service access bay. And what this bay does, keep all is needed for the instruments or for the tools to work correctly. And however, those parts, they require walking through and several times, and also they require a lot of maintenance, and they have a lot of oil that can come out the pump, so that's considered a contaminant. So we put in an area that is just close to the clean room, but it cannot be kept as clean as inside this area. The second bay is the bay where it's dedicated to gallium arsenide, and as you see in the edge, there's a gallium arsenide oxidation, and here on the left, there are 3 types of evaporators. This area is dedicated to metal evaporation and 3-5 oxidation. We separate processes based on the cross-contamination that we can have through the material. As you notice, there is another chase here on my left, and this chase is basically the surface chase to what we call the chemical area. This is probably the most dirty area in the clean room, and this is pretty much our inspection analysis area. Some dry etching. Also, as we see at the end, we have two fundamental tools in this area, and one is single wavelength spectrometer, ellipsometer, and multi-wavelength ellipsometer. These are very, very useful for film analysis to understand the properties of the material after they've been either fabricated or after they've been processed. This is, as you can understand, there is a lot of safety ongoing in the clean room, especially because we are exposed to high voltage, we are exposed to chemicals, and finally, as we see, the most important part of the clean room is what we call the lithography area. The lithography area is a very nice, clean environment. We are certifying this area class 100 compared to the other three areas we have seen, which are class 1000. And here is actually our photography area where we define devices at the micro level, and so we define the geometries of those devices in order to be eventually processed, etched, or metal coated, which they can be served to analyze the characteristics of the material, to analyze the properties of the material from the device perspective. This area usually contains a lot of solvent, and it can be very extremely, if there is an accident or a fire accident, most likely can happen in this area. So as we have seen all the clean room now, we walk out and we go back to the same point that we were before, which is called the gowning area. And as you notice, there is a reason why my wall is always gentle and very linear. It's because I don't want to break the laminar flow, the laminar airflow, and so I'm not creating a turbulent flow. I will also allow the filter, the ABO filter, which filter the particle in the clean room to work efficiently. You also notice that we have always a control system, a swipe card system, to be able to go in and out the clean room.
Hi everyone, my name is Francesca Cavallo. I am an assistant professor of electrical and computer engineering, and I'm also affiliated with the Center for High Technology Materials at UNM. At the undergraduate level, I teach circuit analysis 2, microelectronics 2, and materials and devices, and additionally I offer undergraduate problem courses, which are like more closely related to my area of research. My expertise is in material science, optoelectronics, and microelectronics, and my group specifically deals with ultra-thin materials such as graphene and single crystalline semiconductors. So we synthesize the materials, we characterize them, we try to understand their novel properties, and we apply wherever they seem to be most useful. And examples of applications are high performance, durable and flexible solar cells, powerful sources of very high frequency light, and flexible electrodes to record the electrical activity of the nervous system. Welcome to the Cavallo Hybrid Integration Lab, or CHI Lab. So this lab is divided in two parts. So here in this area of the lab, we fabricate our ultra-thin materials. So we do this under this hood here. And then in the other area of the lab, we characterize our materials. So we have here an optical microscope to inspect the quality of the ultra-thin films. Here we have a workstation where we can do also simulation of various properties of the materials that we fabricate. And here on this other side we have a Raman and photoluminescence microscope, where we again characterize the ultra-thin films, so we determine their chemical structure and physical structure at various stages of the fabrication process. And here finally we have a bench where we fabricate stamps and soft materials that we bond our ultra-thin semiconductor to.
Hi, I'm Professor Daniel Fiesel from the Electrical and Computer Engineering Department. I'm an associate professor, and I typically teach undergraduate courses associated with semiconductor materials and devices, so ECE 371, which covers basic semiconductor properties as they relate to electronics and optoelectronic devices. I also teach the optoelectronics undergraduate course ECE 475. In terms of graduate courses, I teach a graduate course on optoelectronics and a graduate course on semiconductor lasers. My research group at UNM is associated with the Center for High Technology Materials, and my group works on wide bandgap optoelectronics and power electronics. Some of the applications for our research include solid-state lighting, optical communications, and power switching.
Hello everyone, my name is Morteza Monavarian and I'm a postdoctoral fellow at Center for High Technology Materials. My major research is on growth and fabrication of light emitting diodes, laser diodes, vertical cavity surface emitting lasers, and many cool stuff in optoelectronics. So this lab is dedicated for growing these materials from scratch. So if you see this reactor, it's actually called metal organic chemical vapor deposition system, and this is used to grow gallium nitride materials and its alloys, and it can be used for many different optoelectronic applications as well as electronics, high power transistors, and many other applications similar to these. So this reactor can be used for growing the material on top of different substrates like silicon, sapphire, and so you can reduce the cost by using cheaper substrates such as silicon or sapphire. And so the way that this system works is simply by managing how the gas is going to the reactor, and as you can see here, it's actually lighting up. It's because the susceptor is being heated and it's rotating 1500 RPM, and when the gases go there, they start to crack. Let's say nitrogen from the ammonia cracks and gallium from a metal organic source cracks, and then they react on top of the surface and form the gallium nitride. And depending on what sources you introduce, they can form different alloys from indium gallium nitride to aluminum gallium nitride, and even quaternary alloys like indium aluminum gallium nitrides.
Hello everybody, my name is Marek Osinski. I'm a professor in electrical computer engineering, and my office and my labs are actually at the Center for High Technology Materials on South Campus, which sooner or later I hope you will visit. I have a very interdisciplinary research interests, and my group involves a variety of students at different levels and different disciplines, all the way from high school students through undergraduates to graduates. In fact, for undergraduates who are minority students, we have a special program from the Navy that supports research involvement for those students. So think about it, maybe a year or two from now, you might be knowledgeable enough to actually contribute, and I'll be more than happy to talk to you at any time. Our research is very broad. It ranges from optoelectronics, silicon photonics, semiconductor lasers, to colloidal quantum dots and their applications in various fields for nuclear detection, for biomedical applications. We also work on memristors, which are novel electronic components for neuromorphic computing. We also started work on quantum information processing, quantum computing, and novel devices for those applications. So I'll be more than happy to talk to you on any of those topics in more detail if you're interested.
My name is Nathan Withers. I am a postdoctoral student, so I have a PhD, and I'm going to show you around what our Lab 169A, which is our optoelectronics and packaging lab. So packaging is a really important concept where you have lasers, but the lasers themselves are very difficult to see. One second. So you might not be able to see it in here very easily, but those tiny little specks are lasers. It's kind of hard to hook up wires to them. So we use different equipment. So one piece of equipment is this piece right here, which is what's known as a wire bonder. And this uses wire that is thinner than a baby's hair. It's 25 thousandths of a millimeter across. I'll give you an idea how small that is. If you look really hard, you can see the wire, but it's really hard to see, especially with the cell phone camera. This piece of equipment here is what's known as a spectrophotometer, which is different than a different piece of equipment called a spectrophotometer. What this does is this measures fluorescence. So like if you have a fluorescent marker, what is the color of the fluorescence? What color light makes it fluoresce the best? How efficient is this fluorescence? That's what this big machine here does. Because when you make something, you need to figure out what's going on with it. So let's go over to this piece of equipment over here. So this piece of equipment, this thing right here is what's known as a cold finger. And so we're able to get this very, very cold because we do a lot of testing of lasers, and when you change the temperature that a laser runs at, it changes differently. To get you an idea of how cold this is, we use a term called Kelvin, which are like degrees Celsius. They start at 0 Kelvin, which is basically absolute cold. We can't get it down to 0 Kelvin. We can only get this down to about 12 Kelvin. But to give you an idea how cold that is, the surface of Pluto is a balmy 50 Kelvin. So this gets very, very cold. And then we have some optics here for the laser light to be collected, and it goes into this detector here. And then here, all of these wires are we have a bunch of electrical connections in the cold finger itself. So we're able to use all of these different components up here to electrically characterize it and put it into a computer. So there's some electronics, there's some optics, there's programming, and it all has to work together. All right.